And the first talk is by Vincent Cohen-Addad. He'll tell us about sublinear algorithms for Euclidean clustering and correlation clustering.
All right. Thank you very much, Eric. Hi, everyone. Welcome to the session. If you're like, it's the end of the week, if you're over your jet lag as I am, that this is early, so I appreciate the effort of coming around. Okay, so yeah, this is joint work with Chris Strigelson, David Salpik, my student for the Euclidean part. And I'm going to go into the papers. These are a bunch of papers at New York ICML last year. So, I'll point you to the relevant paper if you have questions, but also feel free to interrupt and ask any question you have. All right, cool. So this talk is about clustering, and we're going to see, we're going to have a very liberal notion of clustering here. We're going to say that we have a data set. And I'm not really specifying what that means to have a data set. It's just a bunch of data points. And a data point could, and what we would like to have is like a partition of this data set into group of data points that are similar to each other. Okay, so you just want to partition this data set and pair of elements that are in the same group are similar. Cool. So there are two ways to instantiate the statement. You can have the similarity between the elements be represented by a distance function. So the further away the points are, the less similar they are. Okay. Or you can have like a notion of similarity, which would be like, the higher the value of the similarity, the more similar they are. Okay, cool. So two examples that will be interesting for this talk is the first one is like, and we have a bunch of paper on that, which is a cute, instance of this problem. You have like a state, so you have to guess which state that is. You have a state, and you want to partition it into regions so that these regions are like convex, connected, and they points that are close geometrically are in the same region. Okay, so this is we have papers like, for example, redistricting questions where you would like to partition your space into electoral districts. Cool, and you can see that you want to partition your data points into points that are close to each other, but you may have extra constraints, the cluster should have roughly the same sizes and things like that. So I'll come back to that. And also maybe one thing to realize here is that the number of data points is really huge, but the number of clusters you look for is not so big, right? you don't have like 1,000 districts in one state. Okay, cool. Another instance of this is you have, it's slightly more abstract. You have like data elements, which are maybe images, text, music, whatever you want, stuff we care about at Google. And now you have a notion of similarity between these elements, and you would like to find a way to, group them into, ducks and not ducks, long ears. All right, cool. So then we can look at Euclidean metrics, which is like the first instance of the previous slide, where you have points in some Euclidean space. The distances are the similarity is measured by distances, or you have graphs where you model your similarity through the edges of the graph. All right, cool. So for these talks, I'm going to start with Euclidean clustering, and I'm going to follow Eric's notation, or I think hopefully. I'm going to follow what Eric said yesterday. So if you missed Eric's talk, that's no big deal. Here's the problem I would like to solve in Euclidean space. I'm going to given a set of points in this Euclidean space, and I want to find a set of k representatives in the Euclidean space as well that are cocenters, such that the size of the set is k, so that's the hard constraint. And we minimize the sum of the distances from each input point to the closest representative. And we take this to these powers. And here, you can take the P norm, it could be like the L1 norm, L2 norm, whatever. But for this talk, let's think of P equals 2, it's the Euclidean distance. All right. And now when you set Z equals 1, you find the k-median problem. When you set Z equals 2, you find the k-means problem. And you can look at other powers of P. I'm going to come back to that. But essentially, that's the type of problem we are interested in. Okay. If there is any question about the problem, feel free to stop me and ask. Cool, good. So now let's try to design a sublinear algorithm for this. But we have to agree on some things, on some assumption first. Okay. So what do I have to agree on? So what's the solution size? The solution size, what we are looking for are these k centers in RD. Okay, so the output size are k points in RD. So you have better give me like, if you want me to give you the solution, you have better give me like, KD space, right? Because if you don't give me KD space, I can't even give you the solution, right? So just give me this money for the memory. If you are interested in just the value, then you might be able to do better. You may come back to Eric later on after that. He has some paper on that. So, but if we are looking into, solution here, space is key. Okay. Now, there is some phenomenon that is a little annoying here is that, if you give me a set of points and like, there is one point that is like super far away from everything. And, essentially like n-1 point here, and then something infinitely far, then to get any good approximation to the problem, I need to find this guy. So it's really like a needle in a haystack. Like you have n point, one of them really matters because it's super far away. So if you are not promised that there is a good solution with balanced clusters, you can't really do anything. Okay, so. But remember, for example, for the redistricting problem, you're looking for balanced clusters because the district should be balanced in the number of points. So there are problems where actually the solution has to be balanced. Like you're looking for a solution that is balanced. Often, in practice, if you give me a cluster with 1 point, it's not super useful. It's like, just an outlier coming maybe from the error measure. So it's not too bad of an assumption. I think it's a reasonable assumption. Okay, cool. Now, so the assumption we make for this is like opt clusters are roughly balanced, are balanced size. And we look for running time of like theta kd. Okay, these are the things we need to agree on. Okay, so now I'm gonna make a little jump here. And I'm gonna say that, okay, if this is your assumption, then in fact, the problem boils down to solving the 1Z clustering. There is kind of a reduction here going on. I'm not going to dive too much into the details, but I'm just saying like, okay, if you really want to solve that problem, it's in fact enough to get sublinear time algorithm for the 1Z clustering. The 1Z clustering is exactly what Eric talked about yesterday. You have a bunch of points and you would like to approximate the one center case, like one case, and you are paying the Z's power of the sum of the distances. Okay. So for this talk, I'm just going to focus on the 1Z clustering just to make things simpler. Okay, and cool. So far, so good? All right, cool. So this is, I learned that this is called the power mean objective. Power mean objective, which is like this 1Z thing. And the question we're going to look at is how many points do you need to get from your input? Do you need to look at from your input to get a 1 plus epsilon approximation to the power mean of the whole input? Okay, and here we have to be very clear on something, which is that I don't want to I won't be able to approximate the sum of the distances to the power mean, because again, if I have one guy in my input that is extremely far away, maybe he will not change too much the power mean, because like, if you look at the one median, the one means, the proportion, like, if you have one guy that is far away, it's not going to change too much the location of the solution, but the sum of the distances are going to change. If I have like n minus points at the same location and 1 point at distance 1, the sum of the distances is like, 1. If I don't have this guy, is like 0, so there is a big gap, but the location is not changing too much. So what I'm interested in this talk is actually the location, not the value. Okay, and again, the value I can't really.
So are you thinking of Z as being somewhat small? Or
yeah, constant Z, exactly. Yeah.
Still, even if Z is 2, then the optimum will be the mean. So 1 point really far away will move the optimum by a
Right. But yeah, exactly. But okay, good. That's right. But yeah.
Well, maybe we should repeat the question for people on Zoom.
So yeah, so I'm repeating the question. So if I have 1 point that is really far away, it's going to change a little bit if it's really infinitely far away, then again I'm kind of like I can't do much on that. But what I want to find out is one center. Okay, so good. So the question, very good. So yeah, let me repeat once more the question. So if I have n points at distance 0 and 1 point at distance infinite distance, then the point is going to move to the infinite side, right? So again, I won't be able to. But now, maybe one thing I'm interesting is that still, if I output the mean of the zero, like if my solution is at 0, then it's still a pretty good approximation of the, like, I want to approximate the location of the mean. I don't want to compute it exactly. I can't do, that's a very good low bound for saying that I can't do an exact computation. I can't find exactly the mean. But let's say in this example, if you have this point that is very far away, if I locate the mean solution at 0, it's still a pretty good solution, right? Because, it's a 1 plus epsilon approximation. In fact, it's a pretty good 1 plus epsilon approximation. Even if the mean is actually far, it's, because I have endpoints here, it's still a pretty good approximation. So I can still approximate the location. I can't find it exactly for the exact example that Daniel gave, but, I will be able to do something. The value itself, I'm screwed, definitely. Cool. And so what we are interested in is, like, how many points do I need to get somewhere? Cool. And any other question, actually? Cool. Okay. Good. So why power means? Okay. So this slide I stole from my students. So I will confess some stuff. But like, yeah, it's max likelihood estimator of a generalized normal distribution, to the power z, if you look for the max likelihood, it's going to be like the power mean. So, and, as you take z larger and larger, you will be able to kind of approximate the minimum, like, it's giving you some approximation to the center of the minimum enclosing ball. But again, like, if I really want to have the exact minimum enclosing ball, there's this needle in a haystack problem that is showing up again. Okay, cool. I removed it from the slide because I wasn't really sure about that. But apparently in LaTeX, there is like in LaTeX there is like an algorithm that uses z equals 3 for line breaks. So that's a finding of my students. So I have I don't endorse it. So I invite you to check that, but don't come on me. But it seems that z equals 3 is actually used in practice. Cool. All right. So how do we approach that? So one way to approach it is to this notion of coreset. This notion of coreset is extremely basic. It's a very natural notion that I think has been discovered in many different areas of CS. If you go to, for example, FPT people and you tell them coreset, they don't know what you're talking about. If you tell them kernels, they say, oh, kernel is a very nice thing. It's more or less the same idea under the hood. It's like saying like, okay, you have a parameter, here is going to be k, the number of centers, or it's going to be 1 for us because that's it. Like, I know it's, and you want to reduce the size of your problem to something which is a function of this parameter and not n anymore. So there are very nice coresets for, like, vertex cover or this time, so kernels. I'm trying to, but for vertex cover. And here we are looking for like some sort of approximate kernel for this k-means problem. And the notion is extremely natural. You are given this set of point A, which is your input set. And what you're looking for is an output set omega, which we're going to do weighted. And we're going to say that, so weighted in the sense that there is some multiplicity of the points in this output weight, or omega. And what we are going to do is like, we are going to say that it's a k epsilon coreset if for all solutions, so for all set of k elements, this is a solution. We have that the weighted cost, which is like, seeing the points as with multiplicity. The absolute difference between the weighted cost and the actual cost. So both the sum of the distances from the omega points to the solution versus the cost of the a points to the solution, they are very close. They are within a 1 plus epsilon factor, essentially. Yeah. Yeah, exactly. It's the K of the KZ clustering. That's the question was whether the K is the KZ clustering thing. Yeah. So exactly. So for us, we can think of it as K equals 1 if you want for now. Okay. So we just want to make sure that for any choice of one center, it's the same. So a very quick example. If the green points are your input points, the red points are like your coreset points. They are weighted. Now here's a solution with 2 centers, K equals 2. The sum of the distances here has to be more equal than the weighted sum of the distances. So the red points that is on the top with a 4, the distance is going to be counted 4 times. Okay, cool. And this we want to hold for all possible choice of 2 centers in RD. Okay. So again, here you can see that in this definition, if I can compute this in sublinear time, I'll be again lying to you because this is preserving the cost. And as I said before, like, we can't preserve the cost like this. We can't do it. So we have to relax it. And so we have this notion of weak coreset, which is not exactly what was before, but like, in fact, what we are looking for is like, set again your input A, weighted point set omega, and we're going to say that, it's a weak coreset if for any solution, so here k equals 1, so for any point C prime, which is in my solution, it's just k equals 1. The cost for this is, if this solution is a 1 plus epsilon approximation for my coreset, it's also a 1 plus epsilon approximation for my input points. So I just want to make sure that, like, I can't tell you anything about the cost. I'm just saying, like, okay, if you output this center, it's a good center for your input points. Okay. That's a weaker notion. Because, but then you can look at your old data point, compute the cost, you will have a notion of the cost, but you can't do it in sublinear time. All right, cool. Good. So essentially, before our New York paper, there was this state of the art, which was like weak coresets of size essentially 1 over epsilon for k equals 1. I'm now focusing exactly only on k equals 1. 1 over epsilon squared times the minimum between 1 over epsilon squared and d, and that was for the mean, or and maybe the median as well. Okay, so these were the state of the art. And what we showed in this newspaper was that you can construct this weak coreset, and the size of the weak coreset is going to be 2 to the order z, 1 over epsilon squared. And you can do it by sampling only like 1 over epsilon to the z plus 3. Okay, so you can compute, you can actually find it. The coreset is not too big, and you don't need to look at too many points to be able to compute this. Once you have a coreset, you can find a solution. You can find a good solution for this by running gradient descent, because the whole thing is like a convex problem. So you can use any algorithm, reasonable algorithm for finding a solution to your coreset point. Okay, so the difficult part to finding a sublinear time algorithm is to actually find which points are relevant here. Okay, cool. So let me give you the naive approach, which is in fact almost the approach we use here, is the following. Let's try to compute something. We're gonna just pick d points uniformly at random, and we are gonna assign essentially a weight of n over delta points uniformly at random. Assign a weight of n over delta. I mean, the weights are not too relevant here anyway, because we can't evaluate the cost too much. But like essentially, let's go with this as an algorithm for computing a 1z coreset. Okay. So that's an algorithm. It's definitely a sublinear time algorithm. I just need to sample like delta point for my input. If delta is not too big, it's fine. So now look at the fixed center S, one solution. Let's say we have one solution, one possible solution. So we just fix this one point. Now we're going to show that we are actually pretty happy, because what's happening is that what's the expected cost for this coreset that we just computed for this one point? Okay, what is it? It's just like, in expectation, it's going to be like, the weight time the probability, like, the probability that, the point is sampled. Okay, so the weight times the distance, because that's the cost in the coreset. And in expectation, we just multiply by for the expectation, we just multiply by the probability that these guys belong to the coreset. And so the guy belongs to the coreset exactly with a probability that is inverse of the weight. So in expectation, we exactly get what we want. Okay, it's just natural computation. Okay, so if I give you one center, you should just pick random points, weight them with whatever you want, the inverse probability, and then you're happy. Okay, so for a fixed center, we are happy. Good, that's probably a good start. Now, the thing is that we want this to hold for any choice of centers, right? Like for any possible solution. Okay, so in fact, what we are talking about now is like concentration, right? Because you would like to be able to say, okay, this is going to be true for that center, but the exact same thing happens for that center. So essentially, you would like to have high concentration so that you can take a union bound over all possible solutions. That would be a naive plus approach, right? Like you would say, okay, now it works for one. I want it to work for X. I don't know how many solutions. Like in Euclidean space, it's actually infinite, right? But for any solution, if I have X solution, I would like this to be true for X Yeah.
I mean, well, it doesn't even work for 1 point. I mean, we have an unbiased estimator, but like, if by the point that infinity could be a high probability, our estimate is not actually close.
Right. So yeah.
Maybe repeat the question.
Yeah. So so what Daniel is saying is that we have an unbiased estimator, but for one center, it's not even clear that this is like strong enough. Like we just have expectation essentially. So expectation is like good for like it's somewhat good, but like we really need like concentration at some point. Oops, did I do something?
Vincent, so
okay, good.
Was it saying that if you could indeed union bound over everything, you would actually be getting the value of the cost, and that's something that you can't do?
Right, exactly. So this is too naive, right? In some sense, it's it's definitely this is not good enough. Okay, so we really need to figure out a way of getting concentration for getting these things. All right, so good. So if I gave you the promise that like no matter which center you like, no matter which solution you had, you could all the points were contributing the same way. All the points are at the same distance from the objective. Then you could try to do, okay, we are sampling, and then, because all the points contribute the same amount, you can apply some sort of like Chernoff bound halving inequality or something like this. You can get concentration by saying, okay, I sample enough points. They all contribute the same amount to what I care about, no matter which center I pick. So I will, the variance is bounded essentially. And so, I directly apply a halving inequality and, I'm done with it. Okay. So that's a good idea, but of course, if I place my center at one input point, then the distance is like 0 for these guys, while maybe the furthest away guy from that point is like paying some distance. So there is variance. There is like we don't hope to have like a clean way of handling the it's not true. Like, this statement is clearly not true again. So it's too wishful thinking here. So what we would like to do is partition the points into groups, okay, such that the points that are in the same group have the same contribution to the objective, no matter which solution I'm looking at. Okay, so if you have like the points that are always close, you can pick them together. The points that are slightly further away, you can make them together, and then you will sample uniformly in each of this group. If you sample uniformly with this of this group, if the variance inside the group is tiny, we are having inequality, we are done. Okay, so this thing is not very well defined, again, because the contribution of a point depends on the location of the actual location of the solution you are looking at, right? So you have infinitely many locations. As you change the location, the contribution of the point is changing, right? It's like it depends on the distance of these guys, so it's not very clear. Good. So here is the way people usually, and we usually fix it here. We fix it here is that let's partition into groups based on a constant on an approximate solution, based on the contribution to an approximate solution. Okay, so let's take a center S that is a reasonable approximation to the best possible center S. And now we are going to partition the points around these guys, around the center, into groups of points that have more or less the same distance. What do we gain? Well, now the points that are in the same group, they contribute the same amount in this approximate solution. So now the variance of this set of points is bounded in terms of this approximate solution. But because it's an approximate solution, if I make an error epsilon here, or like epsilon times the distance between these guys here, it's epsilon, and I sum up over everyone, it's epsilon times the best optimum solution. Okay, so it's epsilon times whatever solution you have, because it's epsilon the best. So if you partition the points into groups, right? So partition points into groups that contribute the same to this approximate solution. Then the error we can tolerate inside the group is epsilon, essentially epsilon times the contribution of the points in the group. Okay, because this is always smaller than epsilon what they contribute. Like, if you sum up over everything, it's epsilon times the cost of the approximate solution, which is, pretty reasonable. Good. Okay, so here is the algorithm and the analysis on the same slide, because it's very simple. So you will pick a random point Q uniformly at random, and that's, it's a good approximation in expectation. You're pretty happy in expectation, so because that's a reasonable center in expectation. So that's your starting point. And then you will sample all these points, that many points uniformly at random. We will do some sort of variance reduction trick here. So points that are too far from the centers, we are gonna remove them anyway, because they are so far from the center that, no matter if we are gonna locate something in the close to the center, the exact location of this guy doesn't matter anyway. Like, we just kind of, they don't really matter so much. So they're not, it's like the example that Daniel gave at the beginning. Like, if I have one point that is really far away, of course, it matters very much for finding the exact mean, but I have so much mass at 0 that, I can discard it. I just look at what's happening at 0 anyway, because that's going to be a good center. So things that are really extremely far, I should just ignore them, because they're not really helping me deciding what's a good center for the rest, right? Like, if I have 99% of my points at one location and some guys there, they don't really help for finding what's the right center. So I can just discard them. And that helps me reduce the variance when I'm going to sample stuff. Good. And then, so that's one thing. So we brutally remove the outliers. And then we are going to define the groups of points that, are at more or less the same distance from Q. And then inside the groups, we are going to sample uniformly. And now, if we have a good approximation, the points that are in the same group, they contribute the same amount to this solution. So they have bounded variance. So we can use uniform sampling, apply like a Hoeffding type inequality, and we are happy with it. Cool. Okay. And then you can solve the problem on your coreset by gradient. Yeah. Sorry? Yeah.
Parameter L there, what's the difference?
So the parameter L in step 3 was different. Where do you use that?
Oh, so exactly. So then we can show that. Good. So then essentially, so everything that is extremely close to the center, we're going to just map to the center. So essentially what we want is that, okay, good. Yeah, that's something. Okay, good. So we have the points that are, we have this center Q. We have the points that are very close to Q. And these guys, they are already pretty well approximated by Q. So we don't really need to care too much about them. And we have the points that are very far away from Q. And these guys we remove for the variance reduction. Now, between these, we are going to partition into these groups. And what we would like to have is a constant number of groups. Because for each group, we are going to sample uniformly. So if we have too many groups, the sample size is going to be too big. So what we have is, the goal is to bound the number of groups for which you want to sample. So you're going to sample like, some poly 1/epsilon points per group. So you really want to make sure that the number of groups is bounded. So we have to get rid of what's going on very far, get rid of what's going on very close, and that's what the way we, yeah. Cool. All right. So then, there are more arguments that I'm not going to go too much into because I don't have time, but essentially you still need to kind of find a way to take a union bound over like, the number of centers you have, because like, we have strong inequality, we can apply Hoeffding inequality, but that's only helpful if you can like, bound the number of solutions you care about. And here there is a new ingredient that I'm not going to dive too much into, but like, Eric gave a very nice overview of this yesterday. You can watch the talk online. It's essentially like, you have infinitely many solution S, but because you have this notion of coresets of size bounded of like poly 1/epsilon size, you can argue that, and again, going through maybe Eric's argument, you can also argue that now the problem is intrinsically low dimensional. It's very like, the ambient dimension, it's not very well defined what I'm saying, but like the dimension of the problem, the dimensionality of the problem is only constant because you have only a constant number of points you really care about. That's by the existence of this core set, if you want. So essentially, if you can assume like this low dimensionality of the problem tells you that there are not that many solutions that really matters, because you can look at it in the low dimensional Euclidean space, grid the whole space, and these are only the centers you care about. And essentially, okay, this happens only in the analysis, right? So we can show that the number of, essentially one thing we can show is that the number of centers you need to union bound over is the number of centers you have in this projected space in poly 1/epsilon dimensions. So it's not too crazy. Okay, good. So let me move on. So the main argument is like small number of interesting solutions with this low dimensionality of the problem. And we are using here, I didn't go too much into the details, we are using chaining, like, to be able to kind of have good control over the variance. But essentially that's it. Okay, so that's the recent work for Euclidean coresets. So we have, getting rid of the dimension had been a very, long line of work. People invested a lot of time. Now we have like good ways of dealing without getting rid of the dimension. And we are essentially down to this bound, which is k over epsilon squared, which this is the right bound, by the way. And but in our last paper, we're still carrying around this, mean between k and 2 to the z and 1/epsilon to the z. So it's not quite tight. So there's a very cute open question here. We have this new upcoming paper where we kind of handle constraint. Like, if you have a capacitated clustering problem, you have to handle more like, constraints that, the clustering you're looking for is always capacitated. So each point is not necessarily assigned to the closest center. It's assigned to a center in such a way that you make sure that your cluster at the end of the day are equal size. So if, getting a coreset for that is another question, like, can you really do it? So we have this type of result in this upcoming paper. It's really using morally the similar framework to what I've given you here with more ideas, but essentially that's the spirit. Cool. And there are this line of work for other metrics, because it's very cute question, right? Like it's the size of the coreset really depends on the metric, right? Because if you have very bizarre metric, it's not clear that the number of, there is this union bound question, right? Like the low dimensionality of the problem, this union bound idea that like you can union bound over few number of centers in few number of solutions. This is something we have to deal with, and so then we can get different bounds for different metrics, and getting the right bound for the different metrics is interesting. It helps you understand the metric, help you understand what you can do by sampling. So it's a pretty cool question. Cool. Yeah, so these are the two challenges, like, closing the gap for Euclidean. And I think coresets are like, a little bit underused right now. Like there are some paper on set cover, submodular optimization, where you want to, reduce the size of the problem to some function of k, log n, and so on. I'm sure they can be used for like, more problem in statistics, other setups. So it would be cool to see these ideas used further. All right, so just, yeah. So if there is any question, feel free to ask. Otherwise, I'm gonna move like for the next 10 minutes. I think I have 10 minutes. Yeah, please.
So maybe I missed it. How did you assign the weights?
Good. So for the, good. So for this non-sublinear coreset, for the non-sublinear coreset, we essentially assign a weight, which is the inverse of the probability, the inverse of the probability for sampling the given point. For the sublinear coreset, we ended up not needing weights, because the weights are here for like the scaling factor, if you want, like in the sense that you are sampling k points from n points. So if you just compute the cost, it's not, there is a scaling issue, right? If k is 2 and then you have poly k points and n is super big, it's clear that the cost can't be the same. So you really need this thing. But for the sublinear thing, we show that you don't need it because we're looking at weak coreset. So you just want to find the solution that is good for the coreset and make sure that this solution is good for the original thing. But since you don't need to preserve the cost, you actually don't need to use weights.
Sure, thank you.
So in the algorithm, when you mentioned that you make these groups based on how much they contribute. So since you're starting with an approximate solution and then making these groups, does it matter which approximate cluster these groups come from, or could I suppose, just as a thinking tool, what would happen if I, or is it possible rather to take each approximate cluster, put each of them on like different threads, and is it possible to run your algorithm in parallel on each of the approximate clusters, or do they sort of depend on each other and you have to?
No. Yeah, I mean, like, yeah, if you want to really get the best bound for this coreset bound, like for like, no, not sublinear time, but like the best non-bounds, they are not so parallel in the sense that you have to sample, like the groups are formed across different clusters. So, so it's not like you can find your clusters and do something in each cluster. You will lose in the size, in the total size. You will get a k-squared size coreset instead of exactly k. Like, you know, you'll lose a little more if you do it in parallel. Okay. But yeah, you could presumably do some part in parallel if you don't care about the exact size.
So the groups will be maybe a union of different of these contribution things from various clusters?
Exactly.
Okay, thank you.
Sure. Cool. Cool. So I have 5 minutes, but I think I can make some yeah. I want to give you like it's a very cute algorithm, so I want to give it to you because I really like it. So we are now back to graph clustering. And if you didn't like the coreset, now it's okay. You can think about something else. It's a very cute thing. It's a graph clustering. So now you have a graph, you have edges, and the edges indicates whether two elements are similar or not. Okay. And now we want to find clusters, group of vertices, such that you have a lot of similar pairs inside and few similar pairs outside, across clusters. Cool. So we have this correlation clustering problem where, you have a complete graph. Each edge has a label, which is either plus or minus. And you want to find a partition into as many clusters as you want. K is not fixed now. K is up to you. You have to choose. And you will have this partition into k clusters, and the cost is like you sum over all clusters. If you have a plus edge across clusters, you will pay 1. If you have a minus edge inside a cluster, you will pay 1. Okay, and you want to minimize this quantity. Okay, now let me just, for the sake of this talk, just make sure that we just don't care about the minus edge. We just look at edges. These are the plus edge, and we assume that no edges are minus edges. Okay, so when I talk about the degree or like something like this, I just care about the plus edges. Cool. All right, and we have this very cute result. So what's known about this problem? It's a very famous classic combinatorial optimization problem, which is very cute. There is a pivot-based approach that I don't have time to go into the details. It's a very cute algorithm, 3 approximation. You pick a random vertex, you put all the plus neighbors in, and you form a cluster, you recurse on the rest. There is an LP rounding 2.06 by Shola, Makarichev, Schramm, Eroslatov in 2015. You solve an LP and you round it again. And the integrality gap is 2. And we have this cool result here that it's a different talk. I would be very happy to give, where we use the Shirley-Adam hierarchy, LP hierarchy, to break this integrality gap of 2, and now we are down to 1.994. I mean, obviously this is not the right constant, so any idea for improving this is very welcome. But essentially we show that Shirley-Adams helps you get around this integrality gap. Okay, so it's a cool thing. But now here I'm interested in sublinear algorithm. So what does it mean to be sublinear algorithm? Again, we have to agree that you're looking for a clustering. So you want a label for each point. So give me memory n, right? The thing is that the input size is n squared because it's a complete graph, right? So when I talk about sublinear algorithm, input size is n squared, output size is n, so let me output n labels. Cool. So it's a very nice problem. Like the number of clusters is really up to the optimizer to decide. So it's very nice to not enforce it as a constraint here. It has nice properties. But one thing is that if you just care about getting a constant factor, a very, very bad constant, but like just really a constant factor approximation for this problem, you can realize that the clusters, they must be essentially cliques of plus edges. Because if you have like 1% of your edges that are minus, then I can make everybody a singleton. I'm already paying 1% of the edges, right? So if I make everybody a singleton, all the plus edges will become costly. You will pay 1 for all the plus edges. And it's only like, 100% time more, so I'm losing a factor 100. It's only a factor 100 more, so I'll just lose a factor 100. So if I have like 100, like 1%, I lose a factor 100, I make everything a singleton. So I'm really looking at like, extremely dense cliques. So these are the clusters we are interested in, like, very few outgoing edges, because if I have too many outgoing edges, again, I'm paying a lot, so I can make everybody a singleton. So now I, want something like extremely dense, almost clique. I want to partition my graph into quasi cliques of plus edges. So good. So in fact, if that's what you are trying to achieve, you can do the following thing. Take 2 vertices UV. You know that they are in the same cluster if the symmetric difference between the neighborhoods of the plus edges are almost identical. Like, they must be exactly the same up to, an epsilon fraction maybe of this. Okay. So what we can show is that there exists another one approximation to correlation clustering, so that for any UV in the same cluster in that other one approximation, the neighborhood, the symmetric difference between the plus neighborhoods is extremely small, is extremely small compared to the size of the neighborhood. Okay, because if that's not the case, 1 is not really contributing so much to the clique, to the dense clique area region. So we're going to say that these 2 guys are in agreement if they are like, very close in terms of like, symmetric difference, like, the symmetric difference is tiny. We're going to say that they are in agreement. Okay. So now, here's the algorithm, and I'll be almost finished. You can discard all the plus edges UV such that they are not in agreement, because we just agreed on the previous lemma that, pair of vertices that are not in agreement, they're not in the same cluster. So we might as well discard these plus edges. We might assume they are minus edges. We are not in the same cluster anyway. So let's be upfront about it. Like, just set them as minus edges. And we're going to say a vertex is light if at the previous step, you kill many of these neighbors, because that means that in fact this guy, he had many plus neighbors, but in fact all of these plus neighbors, they are not there. So you're shooting for a constant factor approximation. So if you lose this way, if you lose a constant fraction of your degree, you know that this guy, you might as well make it a singleton. Okay, because if you become light if you lose too many of your neighbors, like they are not, these guys don't want to be in your cluster. So if most people in your neighborhood don't want to be with you, you might as well be a singleton. Cool. So now you just discard the edges between the light thing, because these light vertices, they believe they will be singleton anyway. So if you have 2 light things, they are not going to make a cluster. They don't care. And now you compute the connected component of the resulting graph, and these are your correlation clustering clusters. And that's it. You have a connected component that have diameter at most 4. And so you can even compute that very efficiently in a parallel setup, this is very dense graph of, small diameter. So you are extremely happy. You can do it very efficiently. And, because you are just looking at the fraction of the neighborhood, by sampling log n vertices among your neighbors, it's enough to give you the signal to perform 1 and 2. And so you can really do it in n log n time, essentially. So it's a sublinear algorithm in the sense that for each vertex, you will only keep log n neighbors. And that's enough to run this algorithm and get the constant factor approximation. It works pretty well in practice. I'm not going too much into the details. This has been improved by a lot of people, like, some are in the audience. Now we are down to, we had a very bad constant. Now we are down to 3 plus epsilon in very few rounds of parallelization. So this result has been looked at and improved quite a lot. I'm interested in getting something similar for the weighted case. That would be really cool. Let me just maybe move to the last slide. Oh, yeah, maybe one thing that I missed out a little, like one thing. Okay, let me just one minute for this. So usually we are very excited about differential privacy at Google these days, and these 2 algorithms that I described to you, the Coreset paper and the correlation clustering, they led to differentially private algorithm. Okay, we just tweak them a little bit, and then you can get differentially private algorithm. So I think there is a very nice connection between sublinear algorithm and differential privacy, and it could go back and forth a little more. And in this workshop, I didn't see people drawing so much the connection, but I think it's there. This is an example where it is. So that's really cool. And I'm way over time, so thank you for your attention, and happy to take questions.
Okay, I think we started a bit late, so we could take a few questions, I guess, while Jessica can set up.
Please correct me if I'm wrong, but like in your paper, you had an example of a hard example, right? For this analysis of your correlation clustering.
Yeah.
And for that, the very large approximation factor that you got, it seemed to say that approximation factor was essentially tight because of a certain hard example. So can you say something about like how better? I mean, I know that's not like what you talked about, but like you mentioned that the approximation factor has been improved.
Yeah, to 3 plus epsilon essentially.
So what happens like with the hard example? Is that no longer like a thing?
Yeah, so essentially now the 3 plus epsilon is essentially doing the pivot algorithm that they have. So there will be, it's a completely different way to looking at the problem, because the way you analyze the pivot algorithm is triangle by triangle. And like, for a given triangle, you will say whether you are paying 1 or not, or like this. That's, you will essentially you will phrase the problem in terms of a triangle packing, packing of triangles, of bad triangles. And so the way they look at it is really looking at triangle by triangle and showing that it's completely off from the bad example that we may have. But yeah, it's, on the other hand, it's not, yeah.
So I'm interested in the differential privacy part of this. Do you happen to know what the error bounds are, the best known ones?
Yeah, good. Yeah. So you need, so for the 1Z clustering, again, you have this, I come with my data set and I have this one guy that is super far away. Now I need to be private. So, I must ignore this bad guy for sure. So this can lead to an error that is additive diameter of the input, but it's not tight yet in the sense that what people are getting is like additive the diameter times k times log n times poly something. So getting the right additive bound would be nice. But I think in practice, additive diameter is not too crazy, so maybe that's good. And for differential privacy, for the correlation clustering, like the additive must be n log n, and we have a paper doing that essentially.
Okay, I think we can continue the discussion during the break.
Yeah.